if we take two sets of these ethylene units and we substitute them appropriately with a methylene group in between, we now have a 6-carbon system. And we'll recognize that this particular 6-carbon system is none other than cyclohexane. So if we lay down our cyclohexane this way, we can actually see through the top, we can actually see where the atoms are going to be. And in this particular arrangement, those are all in a plane. And we also notice that if we look at the point of the Newman projection, when we have a boat form, that on both sides, the positions of the hydrogens are all eclipsed. So we have eclipsed on each side, and this gives us the highest possible energy conformation, which we call the boat form. So this can easily make the boat form of cyclohexane. Not only that, but we have available to us, as part of the molecule, we have the Newman projection that goes along with it. But even more than that, we're going to see we'll be able to easily pick out the low energy conformation for this cyclohexane that we have. Now let's take our cyclohexane ring system, turn it around, but now let's arrange it in such a way that the front triangles, from the point of view of the Newman projections, are staggered with respect to what's going on in the back. So kind of want to do it this way. And we can also might want to turn around. This might actually work even better. So we can see carbon in the back is high, carbon in the front is low, and then the other 4 carbons are all in a plane. And we also see that this hydrogen here is staggered with respect to the substituents behind it, as well as this particular hydrogen is also staggered. So we see we have 2 staggered arrangements from the Newman projections. And we can also visualize from the top quite nicely how this makes the chair form. So here's the high end of the chair, the low end of the chair, and here is the part where you'd be sitting. You can recognize right away the symmetry contributions, because here we see that of these specialized prism units, flat, flat, pointy, pointy. When we had them, they were all flat. When they're all flat, we have the boat form. So we can go easily back and forth between the boat and chair forms of cyclohexane just by adapting what we had done for our 3-dimensional Newman projections. We can take 2 Newman projection ethylene units, cross-link them with carbons, and we have a very easy and efficient way to interconvert between the chair and boat forms of cyclohexane. And I had noticed in my reading today that at room temperature, that the chair form is sufficiently abundant that at room temperature there are 10,000 chairs for 1 boat, which led me to think of whether the 10,000 chairs are all on the boat, or that there's 10,000 chairs all alone and there's a boat off somewhere else completely different. I don't know. But it gives you something to think about. So we're all going to do in the next episode after this. I just want to show this because this was a radical change in the designs of the models for ethylene over a method that had worked very well before. So this is a somewhat more flexible method to use, and we can see that in application for cyclohexane it works very, very well. What we are going to look at next episode, we're going to look at more conformations of cyclohexane, and then we're going to go from there to steroids and to applications in biochemistry to show that not only are these methods effective if you're a chemist, they are also effective if you're an architect or if you are pretending to be a marine biologist. So it's well worth knowing this. That's all. It's a very, very short episode today. Just want to get it out to you. Have a good one.